Okay, here we go. Example number 1. We're going to have a buffered solution, and we're going to add a strong acid to it. So go ahead and copy that down. Okay, here we have, what is the pH when 15 milliliters of 0.2 molar nitric acid, so there's my strong acid, is added to a buffer that contains 50 milliliters of 0.25 molar HCO2H, 0.3 molar of that salt that goes with it. Now, we've got 3 different things going on here. 3 different chemicals, okay? So remind yourself with all of these that you get into the beaker and you see what is going on. So let's get into the beaker and see what we have. Okay, with HNO3, I know that that is a strong acid, so I've got hydrogen ions, I've got nitrate ions. With HCO2H, that is a weak acid, so most of it is going to still be all dissociated. Or not dissociated, sorry, stayed together. With my salt, ionic salt, that's going to separate into ions, Na+, CO2H minus. Now I want to cross out things that don't affect pH. Sodium ions don't affect pH because it is the conjugate acid of a really strong base, sodium hydroxide, so it's so weak it's like non-existent as far as pH values, so it doesn't matter. Same with nitrate ions, don't matter with pH values because it comes from a strong acid. Now what I have to work with here is I've got hydrogen ions, which are strong acids. I've got this, which is a weak acid. And these are weak base ions. Okay, now thinking about how to set up, the hardest thing is probably writing out the reaction. I cannot put, partners have to stay, if you remember from the previous slide, the partners have to stay on opposite sides of the equation. So I can easily tell that these guys are partners, so they cannot be on the same side of the equation. So I've got to have either hydrogen, I've got to have hydrogen reacting with one of these two things. Now you should see that if hydrogen ions react with this ion right here, it's going to give me this weak acid. So that's going to be my reaction when I combine all those things together, is going to be hydrogen ions plus CO2H minus, and that's going to give me my product, HCO2H. Okay, so it's really important that you take that process of getting into the beaker and separating out ions and seeing what reaction you're going to have, because that's going to be the most important part in figuring out our stoichiometry. So next, we've got to do some stoichiometry first. Now, we've done ice tables, but ice tables are good with equilibrium and concentration. With stoichiometry, we're going to do more of a BCA table, before, the change, and then after. And I'm going to go through and I'm going to figure out how many millimoles I have of everything here. So for hydrogen ions, that comes from HNO3. So my 15 milliliters times 0.2 molar gives me 3 millimoles of hydrogen. For my CO2H minus ions come from this guy right here. So 50 milliliters. Okay, my 50 milliliters is the combination of both of these guys. So I've got to take my 0.3 molar times the 50 milliliters to give me my millimoles of this ion right here, which gives me 15 millimoles. And then for my weak acid, again, 50 milliliters times my concentration of 0.25 gives me 12.5 millimoles. Okay, next, this is the stoichiometry part. I need to look at which one gets used up first from the reactant side. And so it's all a 1-to-1 ratio here. So I can see that my hydrogen gets used up first. So I'm going to subtract 3 millimoles from each of the reactant side, add 3 millimoles over here, and it's going to give me how many millimoles I have left of each thing. My hydrogen gets used up, so I've got 0. And 15 minus 3, I've got 12 millimoles right here. 12.5 plus 3, I've got 15.5 millimoles right there. So in order to determine if it's a buffer or not, I need to look at what I have. I've got a weak acid, I've got significant amounts of its conjugate base, so I can tell that this is a buffer. And so then, since it's a buffer, I can go ahead and to solve for my pH with my pKa plus log of base over acid. And did I give you the Ka? You would need to look up the Ka value, but the that Ka value is 1.8 times 10 to the negative 4 plus the log of, now here I'm going to use my after the reaction happens millimoles, so 12 millimoles, which is from my base over my acid, 15.5. Remember, with buffers we could just plug in millimoles, it works just fine. And then you get 3.63 as your pH. All right, next I've got 2 moles of NaOH, and you guys can just kind of jot down the things that were given. 2 moles NaOH, a 1 liter buffer solution. It's 0.5 molar of the same stuff, HCO2H, 0.2 molar NaCO2H. Okay, get in the beaker again. Get in the beaker, and so we have NaOH breaks apart into Na plus, OH minus. I've got my weak acid. I've got sodium ions, CO2H minus ions. So what does it matter here? Just the sodiums. Okay? Partners, let's see. I've got, this is a weak base. I'm sorry, that's a strong base. Goodness. Strong base. This is my weak base. This is my weak acid. So I can't put these guys on the same side because they're partners, so they have to be on opposite sides. And then the only thing I can't really have these two guys reacting on the same side either because they're both bases. So I need my hydroxide ions to react with my weak acid. So I get HCO2H plus OH minus gives me CO2H minus and then plus H2O. Okay, that hydrogen goes over there. Now, go ahead and do the stoichiometry for this. If we have, since we're dealing with moles of stuff and they give me 1 liter, then it's actually really easy. If I have 0.5 molar of this acid and there's 1 liter of it, then I have 0.5 moles. 0.2 moles here. Sorry, I wanted this to be 0.2 moles. 0.2 moles. And then I have 0.2 moles of this. Okay, the water doesn't matter. I can tell hydroxide ions are going to be used up first. So I can do -2, that gives me 0, minus 0.2 gives me 0.3 minus plus 0.2 over here, right? Because I'm making more of this product. So that gives me 0.4. These are all of moles. So I have a weak acid. I have a significant amount of its conjugate base. So because I have that, it's a buffer. And then I can go ahead and plug into Henderson-Hasselbalch. pH equals negative log of, and the Ka value I have from the previous section is 1.8 times 10 to the negative 4 plus the log of 0.4 times 0.3. My base is 0.4 moles, and I can just plug in moles because it's the same as the molarity since I have 1 liter of that. And my acid is 0.3 moles. Gives me a pH of 3.87. All right, you guys will be doing lots of practice on these in class today and for homework.